So this is example number 2 for Helmholtz vortex theorem. In this example, what we have is we have a two-dimensional flow, uniform flow. So we have a flow that's coming in this direction. It's completely uniform. It's coming at the initial velocity v sub 0. And this is a very good case of a wind tunnel where we may have we got a big fan here that's generating this flow here. And this flow has been generated here in this section, and there's a flow, and the flow has become uniform as it has moved along. The flow is slow enough that the water surface remains flat. So this is the water surface at the top, okay, and this is going to remain flat. So this surface is not going to move; it's going to stay as it is. So basically, what's happening is, as this vortex, all of a sudden there's a vortex that shows up. This vortex has a value of 1/2 those are the units of the vorticity. So as what it's saying is that this remains at constant at the top, but at the bottom it cannot remain constant. So the question is, can we identify what theorems can apply in this particular case scenario? Number 2, is it possible for us to draw what the surface area, what the vortices will look like at point A, point B, and point C? And is there a way that we can predict what is the value of the vorticity of those points as well? Okay, so let's go and get started in this problem then. And then, so the first thing is all three were Helmholtz vortex theorem applies. Okay, so this is misspelled. This is Helmholtz vortex theorems apply. First of all, it says that the vortex tube is going to remain constant as it moves along. The strength of the vortex tube is going to remain constant along its length. So this vortex tube along this entire length is going to have the same omega-1. That omega-1 is not going to change across this vortex tube. The vortex tube might change its value as it moves here, which we'll see later, but across its length it will remain the same. Okay, that's an assumption. That's what the theorem says. So this is a good consequence. So I'm going to use that, assuming that it remains constant all the way across. So this particular interest from this theory is this particular aspect, okay, that is going to remain constant. So that means that sigma 1 will go, in our case, that's going in this direction, around the entire length, it will be all the same value. Okay, so let's move to the second theorem. Second theorem also applies, because this theorem actually tells me what is interesting is that the vorticity is convective with the fluid and does not diffuse. This is the most important aspect of this. This theorem will apply specifically if this is the ideal fluid, which we can assume it is, and also said the vortex tubes and the line remain coincident with the same fluid in the tube, which is also true, right? So if what we are saying is, if I have my vorticity here, right, I got my vortex tube here, right, and this vortex tube is going to remain perpendicular every single time with this. So in this case, I can assume that's at the bottom because the top remains the same. So now if it has moved to another location, maybe here, it still remains perpendicular with the flow here, but the flow here now has changed its direction. So it's going to stay, it's going to be coincident with the flow, and it's going to change with the flow itself. So now it also applies to number 3, where it says the magnitude of vorticity inside the tube is inversely proportional cross-sectional area of the tube. And we will just do that with numbers, but we will be able to see that as I move along, I have my vorticity here and I have a vorticity there. Now they will have different values. And why they will have different values is because they're going to have different values because this particular rule, number 3. Okay, so we have this information. The other thing that's given in the problem is that your area 1 is equal to 10 inches squared, uh, and uh, this will be h. This distance is h. This is the diameter, so this is pi. Um, so we're going to have an area 1, and it's going to be related to this. So this is the length 1 times h1 times another, maybe the depth of this, let's call it a. And then let's call this is equal to 10 feet. Okay, so this is what we have in this problem. And then this problem here, area at B, we can see that would be h over 2 times A. And so we have the areas now. So the next thing we want to do is we want to see what happens with the vortices. So my vortex here, if you would, is going in this direction. Is a perfect tube. Okay, the vortex got generated as my flow was moving in this wind tunnel. And then as it came here, now there's a 3 degrees, right? And if you remember from the class, because this is rotated 3 degrees, this is going to want to stay perpendicular. It's going to want to stay in this direction. But what it does is, but what it's going to try to do is it's going to try to remain this. So it's going to try to remain at 3 degrees, but it actually, because you need to maintain it, it ends up rotating. So this rotates in this direction, this rotates in this direction. And the reason behind it rotate is because my total circulation at A has to equal to 0. Do you see? Otherwise, this is going to be rotating and it's going to generate a circulation that I do not want any there. So if this segment right here went like this, right, and I have my vortex here. Now this segment, I'm going to exaggerate this segment here. This segment actually rotated now here at 3 degrees. Now my vortex line has to rotate in the opposite direction in order to compensate those 3 degrees and make sure that I do not have any circulation there. Okay, so that's how my vortex line is going to look like. And so it's going to look something like this. There's a vortex line, wait. So it's going to look vortex line, vortex lines. They will do something like this. Here at the top, however, you can see they will remain 90 degrees because here at top, nothing changes. So it comes from here to here. Now my angle is 0. I don't have any angle there. So therefore, my vortex 2 is going to remain at 90 degrees there. And the same thing as it moves along here is also going to remain at 90 degrees. And if I wanted to know what happens here now, well, my vortex 2 is going to do something like this, right? Because this is going to want to tend to rotate. It's going to want to tend to rotate this in this direction, right? It's going to want to rotate this in this direction. This has to rotate in the opposite to compensate. Remember, the idea is that the second theorem always applies and makes sure this is equal to 0. Okay, this is the consequence of the second of the first theorem. That says circulation around it must remain constant. If I'm assuming the circulation is 0, then that has to be 0. Okay, so let's move to the second one. And now it says estimate the vorticity at point A and point C. So what we will have here is the following. First of all, at the point 1, calling this point 1, over B, um, I'm going to have this point right here is HA. So this is HA. Point B will be H over 2 times A. Then this will give you 2, that will be your R. That means that RC is 1 over R. That gives me 1/2. So then we know that my vorticity at B will be my initial vorticity at 1 divided by 2. So my problem said that that was equal to 2. So the value is 2 divided by 2. That's equal to 1 second. Okay. Now we can go from this test section to this test section, or we can just go from here to here. Either way will give you the same answer. So watch this. So if I go, let's say A1 to AC, I have H over A in this section. I have H over A in that section, so that gives me 1. Because it gives me 1 is saying that my vorticity at point 1 and point C is identically 0, because when this is equal to R, RC is 1 over R, and that gives me 1. So this divided by R, this is actually going to give me, sorry, 1. So this is going to actually give me the same value. So this gives me 2 second, 2 second. Okay, so vorticity is actually the same. The other thing I could do is, instead of doing that, I could have come to point B to point C, where this was equal to H over 2 divided by A over 2. This is 1/2. This is R. So RC would be 1 over R. That would give me 2. So now my vorticity at C will be vorticity at B vorticity at C divided by R, which is 1/2. So it gives me 2 times this. This is 2 times 1, because that's what I found here was 1. So that would give me equal to 2. Okay, 1 over second. So you can see the vorticity value that you are getting, you will get the same value no matter what. Okay? Now, the next question, if I ignore the no-slip condition, what angle in degrees the vorticity meets the lower surface at point A and at the upper surface? Well, we already said here, right, that at this surface right here, my vorticity is going to do something like this, right? My vorticity bends. In this location right here at the lower surface is at alpha equal to 3 degrees. And this is because of Helmholtz's first theorem to ensure that your circulation remains constant as I move along. Now, in this location remains perpendicular 90 degrees because nothing is making this change. And this is all the consequence of Helmholtz's first theorem. Okay, so this is how these problems actually work. And this completes example number 2.